What's up, guys? It's Mr. Brengle, and today we're going to be continuing our constant velocity math practice by doing questions 7, 8, and 9. So let's jump right into this. Here, we'll get one more zoom. I lied. We're going back there. Okay, so we're going to start by underlining everything that we know from the problem here and then circling our unknown. So Destiny completes a lab in the physics room. She starts a bowling ball rolling at the left end of a meter stick starting at a position of negative 0.23 meters. Please make sure that we are paying attention to that negative sign. She then has the ball roll several meters to the right until it stops at a position of 3.35 meters. The ball rolls with a velocity of 2.15 meters per second. How long does it take in seconds? So that's asking us for time. So I'm going to circle how long and then in seconds so that we're clear that that's not asking for like a distance. How long in seconds for the ball to roll from start to end? So the first thing that we need to do at this point, or the next thing we need to do, is we need to take all those things that we underlined and assign them a variable symbol, right? We need to match up our numbers with variables, and we'll write those out to the side here. So this is the second point that you will get. This was the first point, and now we've got our second point. Let's write these things down. So it might actually be helpful to start with a diagram because it says that, she rolls the ball this way, and it says that she starts it at a negative position. So if this is negative 0.23, that's where the ball starts. This would be 0 meters. The ball rolls to the right until it stops at a position of 3.35 meters. So we can see that it's going to cover more than 3.35 meters, because if it stops at 3.35 meters, then that means that it covered that entire distance plus whatever distance it covered before it got to 0 meters, right? So just keep that in your mind, that the total displacement of this object is going to be greater than 3.35 meters. That's usually the common error that's made on this problem. So now it might be easier to identify what's what. We can see that the initial position of the bowling ball is negative 0.23 meters. We can see that the final position of the bowling ball is 3.35 meters. We know that the velocity of the ball is 2.15 meters per second, and then the time that it takes to roll is what we are solving for. The third thing you'll get your point for is writing out the equation to use here. And for this one, you just need to make sure that you are using the equation that involves initial and final position, unless you preemptively calculate the displacement. But I'm going to kind of write these off to the side and then I will erase them. Remember that velocity is equal to delta x, or displacement, over delta t, the change in time. But what that really means is that velocity is equal to final position minus initial position over the time interval, which I'll just rewrite as t here. And then we could rearrange that. The other one you have on your equation sheet is rearranged for final position, like this. Okay. And so it really, it doesn't matter which one you use. You might have to do an extra step if you use one versus the other kind of thing. But basically, I think that the easiest thing to do is to look at these equations and either just plug the numbers in if you're not sure what to do, or consider rearranging this equation for time right off the bat. So if I rearrange this for time, I would multiply by time on each side. And so it would become delta x is equal to v times t. And then if I wanted to get t by itself, I would divide by v on each side, and I would find that time is equal to delta x divided by velocity. Okay, so displacement over velocity. So if I use that as my equation, it makes it pretty simple here. I can actually just write either that in, or go ahead and separate it, final position minus initial position over velocity here. If you wrote down a different equation, as long as it's this equation, it's just rearranged in a different way. So not a different equation, but rearranged. That's fine. That's fine. As long as you solve it, you plug the numbers in the right spots and it has all of these variables here, you're good to go. So what I will do is go ahead and get my fourth point now for showing my work. So time is equal to the final position of 3.35 meters minus the initial position of negative 0.23 meters. So we do have a double negative here. I'm going to go ahead and handle that right now. Double negative turns into a positive. And then we'll go ahead and divide that by the velocity of 2.15 meters per second. So I'm going to go ahead and take this a step further. We'll add our initial and final position together here. And we see that time is going to be equal to 3.58 meters. Trying to do some head math here. So over 2.15 meters per second. And then we can go ahead and solve for the time, which let me grab my trusty key here that already has this so we can save some time. And you should get 1.67 seconds. Okay, so I hope that all made sense with manipulating your equation. If you wanted to, you could just use, say, like this equation right here. You could have just said, okay, well, 3.35 meters is final, multiplied by 2.15 meters per second, multiplied by the time, which is what we're solving for, minus 0.23 meters. And then you can see here we would have to add 0.23 meters to each side. So that would be what we did right here, right? We added those things together. And then you're just left with 2.15 times t, we divide by 2.15, and that's what we ended up with over here. So it all ends up getting you to the same answer. It's just however it makes sense for you in terms of manipulating that equation. I'm okay with whatever you want to do on that. Let's go ahead and move on here. 8 and 9 are not quite as involved. So we'll jump right in here to 8. It says peregrine falcon, world's fastest known bird, has been clocked diving downward towards its prey at a constant vertical velocity of 97.2 meters per second. If memory serves me correctly from my childhood, I believe that peregrine falcons can top 200 miles per hour on a dive. Fun fact of the day. If the falcon dives straight down from a height of 100 meters, how much time does it give a rabbit below to consider his next move as the falcon begins his descent? So don't let the fact that this says height confuse you, because if you think about it, we're assuming the falcon is diving down in a straight line. It doesn't say that, but we have to make that assumption. Otherwise, it would be diving at an angle, and that would be a different problem. But we'll go ahead and assume that it has gone straight down. So anyway, let's go ahead and write down what we have here. We know that the velocity of the falcon is 97.2 meters per second. And the height, which is just a vertical distance, right? Like, let's just go ahead and call it delta x, the change in position. Really, we should call it delta y because it's a vertical position, but we haven't dealt with any of that yet. So let's just keep it delta x for simplicity's sake. And we're going to write 100 meters there. And then this is asking us to solve for time. Okay, so third thing here would be our equation. V equals delta x over t or delta t. It really doesn't matter. It's just change in time or the time interval. And with this, let's go ahead and I'm going to plug numbers in before I rearrange this time just to show a different way of doing it. So this would be the fourth step showing our work. 97.2 meters per second is equal to 100 meters divided by t. So we do need to multiply by t on each side, right? This is going to get time off of this side. And now what we have is 97.2 meters per second times t is equal to 100 meters. At this point, we need to divide by 97.2 on each side, meters per second, in order to cancel it here and get t isolated all by itself. So we do need to do 100 divided by 97.2, and that answer should come out to be 1.03 seconds. So I forgot to put this on the last problem, but these are your last 2 points here. T is equal to 1.03 seconds. Box in your answer, and then we would get our extra points. This would be 5 for the number and 6 for the unit of measurement there. Okay, next problem is very similar. According to the World Flying Disc Federation, the world distance record for a flying disc thrown in the men's 85 years and older category is held by Jack Roddick of Pennsylvania, who on July 13, 2007, at the age of 86, threw a flying disc for a distance of 54 meters. If the disc was thrown horizontally with a speed of 13 meters per second, how long did the flying disc remain aloft? So I'm going to circle how long, and I'm even just going to write t next to that because that is asking me for a time, not a distance. There's our first point right there. Okay, second point here, let's go ahead and write down what we know. It said distance was equal to 54 meters. It said that speed was equal to 13 meters per second, and then we are solving for time. Once again, we'll go ahead and we'll put this equation in. Speed is equal to distance over time. This time we can go ahead and rearrange the equation up front. Let's do that. So we multiply by time on each side. If you don't like doing it this way, you can plug the numbers in first. That's fine. These cancel out. Now we're left with speed times speed times time is equal to distance. We now need to divide by the speed on each side to get this out of here, and we find that time is equal to distance over speed. Okay, so you don't have to rearrange the equation to get the point here. You just need to write the either speed equals distance over time or time equals distance over speed. If you write speed equals distance over time and then you plug numbers into the equation, you are rearranging the equation and you're showing me your work throughout that, so you'll get full credit. Fourth step, show my work over here. So the time is going to be equal to 54 meters divided by 13 meters per second. And then time is going to be equal to 4.15 seconds. This would be your fifth point and your sixth point right there. So that will conclude our math problems 7, 8, and 9 on your constant velocity math problem practice. Thanks for sticking with me, and I hope you learned something.